Yeah, so without further ado, so my presentation is on real-time asset tracking. It's basically based on a customer case that we had to implement. So I'd like to kind of discuss those kind of things with you as well. And I did do this presentation a while ago at Tekorama. I don't know was anyone here at Tekorama in Belgium? Yeah, I know Rick was. Oh, excellent. That's good. So this is all new for most of you. Well, actually, Rick, you didn't see my presentation either, right?
I've been looking forward to this one.
Exactly. Awesome. So my name is Joonas. I work as a developer / software architect at Azure. And I've been working with this Azure stuff for around 9 years at this point. I'm an Azure MVP as well. Wanted to include this slide because I thought it's funny. If you want to try to find me in this photo, it's a bit of a Where's Waldo kind of situation because Olli's magnificent face is right in front of me. But yeah, that's our company. We have offices here in Helsinki, Denmark, and Belgium. So for the agenda, first we're going to look at the business case of the thing we had to implement, and as well as the architecture. Then right away we're going to get into the demo, which you can test out as well. And then we're going to talk about the fun topic of coordinate systems. I know, at 9 a.m. in the morning, my favorite thing. And then we're going to talk about a little bit of performance optimizations that we could do here. And we'll maybe have some time for Q&A. If we don't have time, then you can just catch me later after the presentation. Also, if you have any questions during the presentation, just raise your hand. So, the business case. So, we have a customer who has a bunch of what they call assets, but that are essentially trucks, containers, this kind of stuff. And they want to know where those are. They also have a bunch of factories, kind of, those trucks also go into other kind of logistics hubs, ports, this kind of stuff. And so they want to know where those trucks or their assets are at each time. And also they want to know when these assets enter one of these logistics hubs or factories, and as well as when they exit them, of course. And I'm just going to forward this one. And the main thing that we also get from that is that we get statistics on kind of how long it takes to unload at this location, how long it takes in transit between A and B, and so on. Data which can be then used to optimize logistics. So some requirements from the customer. They would like to have a quote-unquote real-time locations of these assets on a map. And the developers in the room know that real time is a relative thing. It depends kind of what the actual requirement is. It's just that when we hear real time, we are like, okay, it needs to have a direct TCP link to the customer's like PC, basically. It's not usually the case. Usually if it arrives within like 1 minute, it's considered a real time. And in this particular case, actually, like 5 to 10 minutes was totally fine, actually, as a delay, so it's quote-unquote real time. The trucks, they don't move very fast. So, yeah, they're not really going to lose them in 5 minutes. The geofences for each location can be any polygon. So remember, we had this like factory area. Well, how do you define what is the area, right? We could just make it a circle, basically make it like, okay, if it's within this distance of it, then it's considered inside it. But we went a bit more fancy. We want to allow whatever polygon, so you can just draw like whatever shape you want around the area. And if it's inside that, it's considered in that. And we want to store the date and time whenever a vehicle enters or exits a geofence. Get some notifications on the map view as well when these events occur. Want to keep these location events as well for a couple months for analysis. Don't need to keep them longer than that. There's also quite a lot of that data. And want to also allow authorized users to change the device configuration straight from the map view. Okay, so for the architecture, just going to go through this kind of piece by piece, so it's a bit easier to digest. So the first part of our architecture here is, of course, we need to get that data somehow to the cloud, right? So we're going to use Azure IoT Hub for that. And it's like, okay, well, we could use something like Azure Event Hubs as well, right? That's also a good service for doing data ingestion, right? But we actually also want to be able to change configurations and stuff. So IoT Hub gives us that bi-directional communication. And then we're using device provisioning service to automatically provision those devices, so we don't have to manually configure each device in IoT hubs. And so DPS, or device provisioning service, the whole point of it is just to make it much easier to register IoT devices at scale. So essentially you configure how they authenticate in DPS, and then when it boots up for the first time, it connects DPS. Hey, I'm this device, this is my authentication, and DPS is like, okay, looks good. I've registered you in this IoT hub. Go ahead and connect there. The one nice thing about it is that you can configure this allocation policy, which basically decides which IoT hub is chosen for the device. And you can make it so that it uses the closest location, for example. So if you have multiple IoT hubs, you can configure it so that it'll select the IoT hub that's closest to the device. And the IoT hub is our telemetry sync, yeah, and gives us that bidirectional communication. So once we have that data in the cloud, we're going to actually forward it to an event hub. Now, strictly speaking, this event hub is not necessary in this architecture. IoT hub includes an event hub compatible endpoint that we could also use. There was a couple reasons. In the actual business case, we actually had events coming from other sources than IoT hub as well. So the event hub was essentially the common place where all of the events came. But yeah, so in this particular sample case, it's not exactly necessary, but we still have it there. And we get the data from there over to Data Explorer, where we're keeping it for a couple months. And then we're getting the location updates to a function app, from which we actually check whether they've entered the geofences or exited them through an Azure SQL database. So yeah, the event hub that we have there is a very, very large-scale data ingestion service. Mainly, the scaling in it is done through these partitions because, you know, I/O and maximum kind of IOPS is a thing. So it splits it to partitions so that you can ingest more data and also process more data simultaneously. One key thing to understand about event hubs is that it is an event log, it's not a queue. So when you process a message from an event hub, it's not deleted. It's basically just a buffer, and the events are deleted when their time to live expires, essentially, from the end. So they're not gone until that. The processing is in order as long as it's within the partition, so you have to choose your partition key pretty carefully. In IoT scenarios, it's typically the device ID. It's kind of a natural choice. Now, ADX, or Azure Data Explorer, it's a bit overkill for this use case. I say this because ADX is what is actually powering Azure Monitor. So, you know, when you run Custo queries against it, you're running them against ADX. They made a blog post about it some time ago where they explained that they're processing something stupid like a petabyte a day. There it's just, yeah. In the business case, we originally used the time series insights. Yeah, RIP. So after we had deployed like 20 of those, Microsoft informed us that they are actually going to kill this service. Thank you. And told us to go to ADX, which was like 5 times more expensive. So, yeah, nice. It is really massive scale, though, and we can do native ingestion from Event Hub. That's like really easy. It was easy in time series insights, too. It also supports geospatial analysis, which is nice. And we could also use Cosmos DB here. The only problem with Cosmos DB is that you will have to very carefully design your model, and you'd most likely have to make it write optimized here because there's a lot more writing happening than reading. And yeah, it's a little bit more complicated. Then we have functions, which is the serverless application platform. How many of you here have used functions? Oh, yeah. Good. Then we have an SQL database. So SQL Server supports spatial data. We can do spatial kind of stuff there as well. The business case already had an SQL database, so we were like, well, we can just use that, right? So that was one reason. But it is also not a bad choice here, actually. You can use Cosmos as well, but I'll get back to Cosmos a bit later. So then we have our front end, essentially here in the sample app. So we have a function app that is containing the front end files. It handles the real-time SignalR connections and all the API calls from the front end as well. So we're using SignalR for real-time communication between the front end and the back end. And then we are using Azure Maps for the map content itself. So we have those map tiles being loaded from there. So in this use case, we only use maps for that. It does have other features too, like if you want to do lookups, basically you can give it a set of coordinates and it'll give you back an address, or you can do it the other way around. You can do kind of point of interest searches and stuff like that. The other really good part about maps was that the billing is within the same Azure subscription instead of having to make like a Google account and having another billing. And in this business case, the customer was a bit of a bigger enterprise and didn't have a Google account also. So basically when they said that, I was like, okay, so we're not going to do that, because I knew it's going to be like months and months of meetings and stuff to get that account. And it's like, no, it's not worth it. Then we have SignalR Service. How many of you here have used SignalR? Quite a lot, yeah. So it's basically for real-time communication over WebSockets. SignalR, when it was kind of invented, the big thing about it was that because a lot of browsers didn't support WebSockets, so it allowed kind of fallback to other methods that would work. But from the developer's point of view, you wouldn't have to do anything different. So it was really good. Nowadays, WebSockets are pretty ubiquitous. So. But the big thing about SignalR Service is that it allows us to scale the WebSockets separately from our backend. So because you can only have a limited amount of these connections in your backend servers, so this allows us to scale it completely separately, and the backends only have a few connections to SignalR Service. Now, in this case, we are using functions, which, as you know, is serverless. So how are we going to do persistent connections? The answer is we are not going to do that. We are going to put this into serverless mode and allow functions to scale to 0 if it wants. So basically, that's how the whole sample architecture looks like. And one change that has happened there is that we now have a container app there instead of an actual vehicle. So just to say right now, a disclaimer, when I show you the demo, they're not actually, actual vehicles. They are simulated. Yeah. So without further ado, let's go to the demo. It's westel.in/igloo demo, or you can scan the QR code. Both of those work. We're going to try not to bring down the Wi-Fi, by the way, when I do this. But it's not that much data. Okay. Yeah, so I'm going to put that on the other screen. Yep. So that's how it looks like, the front end, essentially. So those are the simulated devices. They're going around Helsinki. Essentially, there's 2 routes that I've programmed in there, which they can choose to go in reverse as well. Yeah, so each of those is being simulated there. Let me, but currently we're running container apps on 3 instances, and each of those is running 10 simulated devices. So we're running 30 vehicles at the moment. But I think it would be more interesting to see how that scales. And this is one of the reasons why I picked container apps, by the way, because you can just very easily go here and do something like this. We can say, let's go to 30 instances. So while that is deploying, we can also see kind of what happens over here. By the way, if your mobile device starts lagging when I do this, I'm sorry. Browsers don't necessarily like being bombarded with like 1,000 messages per second from the WebSocket. I've had that happen a few times. Just gonna wait for the container app to scale out. Yep, there we go. I think it started to scale out. Okay, so one problem with this is that now it's maybe a little bit harder to show you what is going on there. But so also we are currently checking these geofences. So Helsinki Station has a geofence here. So whenever one of those is entering it or exiting, we're getting an event here as well. Those are being logged in SQL database as well in real time there. And also something that we can do as a logged in user, I can also go here and just change the parameters, which is pretty fun. Now, because we have a lot of devices there, you're probably not going to see this. So these vehicles turn out to have rocket engines, actually. It's not the prettiest UI I've ever made, by the way. As you can tell, I'm a software engineer, not a UX designer.
Isn't it? Isn't it? I think it might be the prettiest UI you ever made.
It might be, yes. Sake is correct. It might be the prettiest UI I've ever made, actually.
It's pretty nice.
Yeah. And yeah, then so the sample app, and by the way, this is all on my GitHub, so you can get the app there, get the whole app from there if you'd like. It also includes this Azure dashboard, which will give you a bunch of like performance data from the data processors and such. So I think we are. Let's see how many we are processing right now. I think it hasn't updated yet. We were doing like about 1,000 a minute there, but we should be doing tens of thousands a minute. Well, anyway, I'm actually going to scale down this one over here while we are waiting, as I don't particularly. This is the fun part of container apps, the portal. Okay, that looks good. Okay, let's scale it back down. And then we have our device provisioning service over here. I'll just quickly show you how that's configured. So we have an IoT hub linked. You could have several, obviously. We only have one in this case. Then we have our enrollments. So we have our production one here. I have one for local development there as well. And as you can see, we have an attestation mechanism. So this is how the devices authenticate. Here I'm using symmetric keys because it's much, much easier for a demo. I didn't particularly want to start fiddling around with certificates for some reason. But certificates or TPM is the approach recommended for production. And that the main reason is because there's only one key. Well, okay, two keys, but they're like, you know, similar keys, essentially. But what these keys allow you to do on the device is essentially become whatever device you want. I mean, the device can choose its ID. So you can just become another device with that key. So not particularly great for production scenarios, right? It's not the best security. Certificates are kind of nice because you can put like a root certificate or intermediate certificate here. And then the devices just have a leaf certificate, and it all kind of just works. Well, I typically say that with certificates, and typically they don't work just like that, but still. Yeah. And that one is, of course, set to only provision to that one IoT hub always, but you could configure it in other ways as well. We can also look at the devices from here. There's going to be quite a few of them. but I can just show you kind of how the device twin looks like from here. So what we're using for configuring those devices is we're using these device twins in IoT Hub. And you can actually see here there's these kind of, well, the font is pretty small, so maybe you don't. But there is these desired properties over here. One of them is the speed over here. So what we can do is we can just change the number over here and hit save. And the device is going to receive that. And then if I scroll down, you also can see a similar one called reported properties. So these are the properties that the device is reporting back to IoT Hub. So essentially it allows us to confirm that the settings have been actually applied. You can also put other stuff there, of course. And if I, well, okay, so I picked a device that is actually not running anymore, so it's not updating this, but if it was, it would have updated the new setting over there. Then we have Azure Data Explorer over here. Let me just make that a little bit bigger. So one of the neat things that we can do with Azure Data Explorer is that we can also do spatial analysis. So we can, for example, plot those on a map view over here. And then we also have our SQL database. And this is kind of funny, actually. So there's a similar feature in SQL Server Management Studio where you can get these like spatial results. So you can see the geofences over here, and you can see the kind of definition over here, the coordinate points, essentially, for the polygon. But you can also go to spatial results. Now, in SSMS, you actually get like a view, like a picture at this point. But the portal gives you an SVG. Now, what will the SVG contain? Cool. Thanks, Azure Portal. Excellent.
Looks like your UI?
Yeah, pretty much, yes. It looks like my UI. It's not much different. Actually, even the shade of blue might be the same. Yeah, but SignalR. Now, this is kind of interesting because so what we've done here with the SignalR service is that we've changed it from default service mode to serverless, and then we've configured this thing called an upstream. Now, because the SignalR service doesn't have a persistent connection to functions, what it instead has is if there's a message from a client to SignalR service, it will forward that message to our functions through this webhook. So the SignalR service kind of plugin in functions, it kind of provides this webhook for you. So you don't need to actually make this webhook. You just make the functions there kind of with the triggers and stuff that is in the documentation. It's pretty easy to use. Now, one really, really small thing that kind of threw me for a loop here is that there's this hub filter here. So you can essentially filter what is sent to this upstream. And so I've chosen to put the hub here because I have a development and production one in this same one. And this has to be in all lowercase. You can define it with uppercase characters, but it won't work. And then you wonder for about an hour, kind of why am I not getting any messages? But yeah, that was a fun one. Let me check if I had anything else. Oh yeah, actually I do. I do have time as well, so I may as well show some code as well. Okay, now I'm going to make that a little bit bigger, and I'm going to close that. Okay, that is a lot better. So this is from the container app, so from the simulator's code, actually. And one of the things that it does is it does the device provisioning through the device provisioning service. And if we actually look at the definition for that, it's there. That's the whole code. And the big thing about that is, of course, the key that it is using here. And it's just a derived key from the master key plus a device ID. That's it. It's not complicated. And that's why I chose it for the demo. And essentially what it then returns you is the IoT Hub host name to connect to. And then we can connect and start sending stuff. Now, one of the big things that we do initially is that we get the device twin, and we get the initial settings, essentially. and we update those as reported, so we've confirmed we've received them. Then we set this desired property update callback, which is essentially just, hey, call this function whenever there's changes to the twin. And we do the exact same thing again. And then we have our simulator where we are sending events, and sending events is pretty easy. It's just calling send event async on the event device client. Notice that we were kind of having to do a little bit of a data kind of transformation here because IoT Hub and Event Hub essentially just accept whatever bytes. So if you want to send in some other format than JSON, you can. And then we have, might as well just show you this one as well. So we have here we have our function that is receiving the location updates and updating the latest locations on the map and in the database as well. So it has an Event Hub trigger, so every time there's messages in the Event Hub, and it has a SignalR output over there. And one of the big things that I'm also doing here is I'm accepting a batch of events at once, always. Because if you are not accepting a batch, then you are allowing functions to run your processors in parallel, essentially. So I didn't want that. I wanted to have control over it, so I just taken a batch of events at once. The batch size is actually reported to the dashboard. I'm actually going to check kind of how that looked like. So you can see there when I scaled up the container up, we slammed right into the default 100 batch size, essentially. So it did get it down as it started to get through the backlog, essentially. But typically you would see it doing like maybe 10 or so there at most. Also, usually you wouldn't be receiving events for the same device in the same batch because they're like every 5 to 10 minutes, right? The updates in the actual case, but I wanted to make it a bit more interesting here. But yeah, I'm not going to go too deep into the code here. You can check it out if you want. But one thing here is that we are returning from this function, this SignalR message actions, which are with a bunch of parameters. And then those are received, if I can find it here. So the front end is using the Vue framework. I find it pretty nice to use. Okay, I've kind of forgotten where the callback for it is actually, but essentially it ends up here where we get those updates and do a bunch of math to figure out the speed and heading and stuff of the vehicles. There's one reason, by the way, why the app slows down quite a lot when you have a lot of events, because it's doing all that math in the browser, which is not the most optimal place to do it. Yeah, that's it. Anyone have any questions about the demo? Anything?
The problem is that coordinate conversions beginning. You promised coordinate conversions.
We're getting to the coordinate systems. That's right here. That is.
Architecture, was stream analytics ever a choice for like the middle part there?
Good question. So the question was a stream analytics a choice? And you can absolutely use stream analytics as well. The only problem is that stream analytics doesn't have an output to SignalR. They don't have that. If you wanted to have a similar one, you could output to Power BI. They can have similar map views there as well. Well, not with like the custom graphics and all that for sure, but you can do that. But I wanted to do a little bit more data processing here as well, and I felt like the stream analytics wouldn't actually allow me to do that. Also storing the events, because I also have to detect kind of when there's an entry and an exit. Essentially, and wasn't sure how to do that with stream analytics. It might be possible, though. Anything else? Good. So we can go to the exciting topic of coordinate systems. This is kind of important when you're working with location data. I think it's equivalent to knowing how time zones work if you work with time data, essentially, because it's a similar mess, essentially. And essentially, if you're not familiar with coordinates as a whole, I mean, you can just kind of hold your mouse, you can click and hold the location on Google Maps, and you can get the coordinates out of it, essentially. And so that's about 60 degrees latitude and 25 degrees longitude there. Not that Google tells you which one is which. I'm constantly having to check which one is which, actually. And now this one over here. One of my favorite pages on GitHub is Falsehoods Programmers Believe About Time. If you have never read it, I highly recommend it. It is hilarious and depressing at the same time. So I thought I'd make one about coordinate systems. The first one is there's one standard system that everyone uses. Okay, there's a handful of systems that everyone uses. The 0, 0 location is standard. The first number is always longitude. The shape of the Earth is standard. Now, this one is like, okay, like seriously. This is the only like actually physical thing here. Like, really? Yes, really. The Earth's shape is part of the system. Like, cool. Coordinates are always measured in degrees. Continental drift never or always affects coordinates. The answer to that last one, by the way, and most of these as well, is the standard consultant answer. It depends. So if you're interested in checking out coordinate systems and kind of what they look like, you can check the EPSG registry, which stands for European Petroleum Survey Group. Now, this whole thing, like when I started looking into this doesn't really make sense. So an EPSG member created the registry in 1985, and it has never been maintained by EPSG since, but it's still called the EPSG registry. Cool. It's the global registry for coordinate systems, and you can see actually on the bottom there, when I took this screenshot, there were 13,419 systems.
Less than language models in Hugging Face.
Yeah, but still. So the reason for there being a lot of them is that they really are for different use cases. Also, some of them are more precise for certain locations. So there is kind of a reason for that. Like some of them are used for land survey and things like that. Now, if you can choose from these, I would recommend that you use these two. The first one is the one that Google Maps uses. It's the one GPS uses. It's the most common one. It's the one where you see coordinates like every time, essentially. Now, really luckily, these two are super common, essentially. Like in the business case as well, we did get lucky, and the source actually did use the first one, the EPSG 4326, and used that for data storage and calculations. Though that does come with a caveat. If the source data is in a different one, you may want to hold on to that original value as well. Because that 4326 is not perfect for certain things. It is the most general one. It's the one that everyone uses, and it's kind of convenient. And if you have data coming from different ones, then you'll have to most likely convert all of them to this one, essentially to do any kind of comparison between them. The second one, pseudo-Mercator, is there because we need another coordinate system for the map view. The map view is flat. As you know, the Earth is not flat. At least I hope you do. And so we need to somehow project the coordinates to that. So we need another system. And that's the one that, for example, Google Maps uses. It's the one Azure Maps uses. And the map SDK actually does the conversion for you. So you don't even need to do anything. But you may run into those coordinates in some cases, which is very confusing when you see the coordinate for this location is 52,000 something, and you're like, wait, what? Yeah, it's not the same system, so. So I also have a list of fun things that you will run into when working with spatial data. The first one is order of latitude and longitude. You may notice that I actually already flipped them once earlier in the slides. Sometimes you may have a .NET type called point, which takes longitude first. GeoJSON, the data format, also takes longitude first. Google Maps gives you latitude first. And the standard, in fact, is latitude first. Now, okay, so the point type I kind of get. It's an X and Y type. You know, it's not an actual spatial data. Longitude is the X coordinate. It makes sense. But GeoJSON, really? Why? So one funny thing about this is that if you flip them twice, or an even number of times, in your data processing pipeline, it ends up correct on the other end. So
how did you find that out?
So I found that out when all the locations on the map were correct, but somehow they were never entering the geofences. Like those events just didn't come up. And so they were the wrong way in there, but then got flipped when they got sent to the front end.
Two wrongs.
An even number of wrongs make a right in this case.
Four wrongs is right too.
Yes.
Gotta tell my wife this.
And so also another fun one is that, well, so you know you can scroll the map view, right? So you can go all the way to the east and you end up back where you started. Well, the coordinates don't wrap around. In fact, you actually just they just increase. The more you go to the east, or decrease the more you go to the west. So you can actually calculate how many rotations they've done. I'm not really sure what the use case is for this, but it is a feature in the map views. So you get like stuff like a longitude of 500 something, and it's like, well, that's not possible. They just go over the limit. Yeah, it's very funny.
Is it in the future then? Is it in the future then?
No, it's not in the future. That's not how time works.
I hope. I gotta read the false programmers believe about time, I guess.
Yeah, you do. Another fun thing, in that projection, there's some locations that don't exist. So if you have locations around the South or North Pole, those are just not there. The reason for that, of course, is if you ever look at the full Mercator projection, the Antarctica is like bigger than Africa, which is like not true. It's just really, really stretched. So the map view people, they were like, yeah, we're not going to do that. We're not going to show this because it looks really weird. And who the hell needs to look at where stuff is in Antarctica? So yeah, but if you're tracking like flights or something in your app, this can actually be a problem because we do have flights going over the North Pole, for example. So they would just vanish from your map view. So you're going to need to do something a little bit more special for that. Then some performance optimizations. One performance optimization that has already been done in the sample app is kind of a grid square system. So when we're sending these events, well, if some vehicle's location is updated in Japan, and I'm currently looking at Europe, I don't really care about that update event over there. So we might as well kind of subscribe only for the things that we're looking at. And that's what this system does. It essentially splits the map view into 1 kilometer by 1 degree by 1 degree squares, because you know it's a sphere. And then we add the SignalR connection to a SignalR group for each of those squares. And then we always, when we send an event, we send it to one of these groups. And so then only the ones who are actually looking at that will get it. Of course, what it means is that whenever you move the map view, we have to update those groups, essentially. But it does lower the amount of stuff coming to the browser. Now, Cosmos DB. Now, going into Cosmos DB, I really expected it to be a lot better option than SQL. And, well, it kind of is. Similar cost, Cosmos DB. Here, I think it was something like 1,000 RUs or 2,000 RUs in each of the 3 containers. It performed pretty well. It was also pretty consistent. like a lot more consistent than SQL. SQL has these like spikes where just for no reason, it's like, okay, I guess this query took 1 second, and that's fun. But that was most of the time, until we hit the RU limit. The problem with Event Hub processing is that it can be very bursty, and what happens when you slam a Cosmos DB really, really hard? It tells you, go away and try again. What the SDK does by default is that it's like, okay, sure, I'll wait a moment, and now try again. Now, what happens at this point is that because we have a constant load, events just keep piling up in the Event Hub while it's doing this. What happens? It takes another big batch and slams the Cosmos DB again. Runs out of RUs, and this is now a loop of death. It will never recover unless you increase the RUs or decrease the load. There's just no way to recover from it. Or you start discarding events. That's the other option. Autoscale could help, could also be a bit costly.
In this case, of course, you could discard events because you don't maybe care about the vehicle's old position if you have the new one. But then you would have to do processing to identify if there's the new one in the pipeline, and that would be its own job.
Yeah, so we could, for example, be like, okay, if it's like older than this much, then we could be like, okay, yeah, just discard it. And this is something that Stream Analytics also can do. For example, you can say that, okay, we just don't allow events older than this, essentially. But yeah, this is something that happened with Cosmos, and it just felt like it's not the best for this. Or you have to over-provision it, essentially. The other fun thing about this was that I tried to figure out what was causing this, and the metrics, looking in the portal, showed that I'm not hitting RU limits. The RUs were like 30%. I'm like, but I'm constantly seeing 429s from there, so obviously I'm hitting the RU limits. That's because the metrics are per minute average. And I'm hitting those RU limits on certain seconds, essentially, and it's not enough to change those metrics. So that was cool.
That's shit. That's shit.
Yeah, it is. It is bad, but of course, it was my mistake also for not looking at the other metric, which shows the amount of, rate-limited messages.
Yeah.
But still. The other performance optimization you can do here is to change the Event Hub partition count. That's because that sets your maximum parallelism. So essentially, you can only have one instance listening to each of the partitions. So if you have 4 partitions, you can have 4 functions app instances. Now, functions does the scaling automatically, which is nice. Now, one thing about it is that you really shouldn't just set the partition count to maximum of 32, because based on the measurements that I did and the testing, it adds overhead on the listener side. It also makes it scale out and in more often, which causes delays in processing as well. It just isn't worth it. And actually, for a lot of use cases, 4 partitions is more than enough. You're not going to hit those limits there. And in fact, the frequently asked questions for Event Hub says that it should be about, the kind of rule is that it would be about max 1 megabyte a second per partition, the throughput. So you can kind of calculate based on your event size and how many events you expect per second. And honestly, the only way to really find kind of what is best is through testing. The thing that sucks about this is that you can't change the partition count unless you're on premium or dedicated, where you can increase it. We can also do some optimizations in the Event Hub trigger in functions. One of them, which I don't think is going to really help a lot with constant load, is the prefetch count. So this is the amount of events that functions will fetch in the background while it's processing your batch. Yeah?
5 minutes.
5 minutes, thank you. But yeah, it's not really going to help if you have a constant load. Then we have this one, which kind of sets how aggressively function scales, so you can have it scale out faster. Then we have this one, which is how often functions writes to storage the checkpoints. And essentially, because the events are not deleted from event hubs, so the client essentially has to keep track of where it's at in the partition. So it has to write this, and you can make it so that you write it less frequently. By default, it writes it after every batch. But I don't think this one helps that much. But what might help quite a lot in this case is to process events in parallel, especially if you're getting a lot of events per batch. This does lead to a higher database usage, higher all that, but it could be quite helpful. Then we have some bigger architecture changes that we could make. We could move the Event Hub processing to dedicated compute with also persistent connections to SignalR and not use the serverless mode. That would increase throughput by quite a lot because doing the SignalR events over HTTP, not the most efficient thing. And if the number of geofences is low, as it is here, we could just keep all of them in memory and just do the geofence checks there instead of incurring I/O. We could also split the function up to several with their own storage accounts, but that's a pretty minor thing in my opinion. Okay, we have a few minutes, couple minutes for questions, if there are any.
If you have no questions, you can of course approach Joonas later. Let's have a 7-minute break, so the next speaker starts 5 minutes later than the schedule says. So 7 minutes, people. Thank you.